Assalamualaikum warahmatullahi ta'ala wabarakatuh. Bismillahirrahmanirrahim. In this chapter, we're going to be looking at properties of fluids. If you recall in last lecture, we have looked at the introductions to fluid mechanics, whereby you'll be introduced to basics about fluid mechanics, what you're going to be learning in this course, and then the significance of fluid mechanics. Why is it important for you to learn fluid mechanics as engineer? And also, what are the modern trends in fluid mechanics? So, in this new chapter, we're going to be looking at the properties of fluids, right? So, what we're going to cover in this topics. First of all, we're going to look at definitions of property. What is properties? And then we're going to be looking at properties involving mass and weight. These are kind of like more of revisions to all of you, since you have learned part of this in your thermodynamics or in your physics. And then we're going to be looking at properties involving flow of heat. I think this is more of a revisions to you. Then after that, we're going to be looking at shear stress in moving fluids. It is important for us to learn about shear stress in moving fluids, because shear stress actually gives rise to fluids resistance. So if you want to move fluid from one point to the next in a pipe, then there will be resistance due to the existence of shear stress, which is actually caused by viscosity. So the properties of fluids that we're going to be looking at is actually viscosity, right? Then after that, we're going to be looking at surface tensions. This is more related to liquids, because whenever there is liquid, it will actually form an interface between liquid and the vapor phase or the gas phase. So in between, there will be a free surface, which actually will exhibit surface tensions. Then we're going to be looking at vapor pressure. Pressure is important because it's actually related to change of phase from liquid to gas and gas to liquid again. Okay. So in thermodynamics, if you can recall, for water, for example, water actually boil at for pressure of 1 atmosphere, 1 bar, it will boil at 100 degrees C, right? So, but if we reduce the pressure, it can actually boil even at room temperature. So this actually gives rise to some problems which is called cavitations in fluids machinery. So we're going to learn a little bit about the properties of fluid, which is called vapor pressure. And finally, we're going to be looking at speed of sound. This is actually related to compressible flow, whereby there'll be certain phenomena associated with the existence of the speed of sound. Right. So what is property? So we define property as the characteristic by which physical conditions can be described, right? So if we have or some things, so how do we describe the conditions? It's actually by defining its properties, right? Its properties. So for fluids, or for any substance, actually, properties can be divided into two, which is extensive properties and then intensive properties. Right? So if you look at properties of fluids, right? So first of all, we have the extensive properties. Extensive properties is actually properties which is varies with mass. So basically, if we have a property X, this is actually proportional to the mass. So what does it mean? So it means that, let's say we have systems, right? So the property is actually X, and we divide the systems into two equal parts. So the property will also be divided into two, right? That is extensive property. Then we have intensive property. These are properties independent of mass. So meaning that if I have a property Y, for example, so it is actually not dependent on the mass, right? So that means that, let's say I have a system which has a property Y, then I divide it into two equal parts. So the property will, the value of the property will still be Y. So this is extensive property, and then this is intensive property, right? So the we can change all extensive property into intensive properties, okay, by dividing by its mass. Normally, let's say we use, for example, this extensive property X. Extensive property X. Okay, this is extensive, right? Extensive. So if we divide X by M, okay, so normally we use symbol small x. So this is now intensive. So normally we call this specific property, specific values, specific values of X, because we have already divided by the mass, right? So examples of uh, properties, for examples, we have examples of extensive and intensive property. For example, we have a system again. So let's say it has pressure P, temperature T, volume V, enthalpy H, right? Entropy S. What else? Let's say, and then it has, let's say, specific volumes. Okay. So now, if we divide it equally into two different parts, what will happen to pressure? So pressure will still remain same on both parts. Temperature will also remain the same on both parts. Volume, of course, volume will be divided into two, right? Enthalpy also will be divided into two. Entropy also will be divided into two. A specific volume, which we have already divided by the mass, will still be the same, right? So the properties which are independent of the mass, which is the pressure, temperature, specific volume, these are the intensive properties. So these are intensive. Whereas the properties which will be proportional to the mass, for example, volume, enthalpy, and then entropy, okay, these are extensive properties, right? Extensive properties. Okay, so the properties are expressed in terms of its basic dimensions. So the basic dimensions of how we express properties. Okay, generally the four basic dimensions, which are length. Okay, normally we use symbol L, and the unit is meter. And then time, we use T, and the unit is second. Then mass, km, and the unit is kilogram. and then temperature, right? We use T, sorry, this is small t, okay? And then, so it's degree C, right? So those are how we express uh, properties in the dimensions and the units. And normally we always use the SI unit in order to, in this course, we always use the SI units. Okay, so next we're going to be looking at the properties involving mass and weight. Okay, properties involving mass and weight. Mass and weight. Okay, so first of all, basics property, mass density. Okay, mass density, basically we use a symbol rho, right? Okay, I think all books everywhere, we always use rho for the density. And the formula is, you know this already, I've learned this many times. So it's actually mass per unit volume. So mass over volume, right? So in terms of dimensions, so it's mass and volume is L minus 3, right? L minus 3. And the units for mass density is actually kilogram per meter cube, right? Kilogram per meter cube. So typical value of density for water, for example, density of water is actually 999 point something, but normally we use 1000 kilogram per meter cube. So when you solving problem, if the value of density of water is not given, you can always assume that it's actually equal to 1000. But if it is given explicitly that is equal to 999 point something, so you have to use that actual value. For air, okay, typical value for air, the density is 1.23, right? But of course, generally, the density is also functions of temperature. Next property is specific weight. So specific weight, okay, specific weight is normally we use the symbol gamma. So specific weight is defined as weight per unit volume. Okay, so the formula for gamma is weight per volume. So weight is actually mass multiplied by gravity per volume. So if we rearrange that, so mass per volume T. So it is also equal to density multiplied by gravity. Okay, so the dimensions for specific weight is, if we look at this, so mass is m, and the acceleration due to gravity is L t minus 2, and the volume is L minus 3. So we have m, so this will cancel, becomes 2, so m L minus 2, t minus 2, right? And then the unit for specific weight is, if we use directly from here, that's actually kilogram per meter squared per second squared, right? Okay, or it's also equal to, because it's mg divided by volume, right? So mg is basically in terms of Newton, so Newton per meter cube, right? Newton per meter cube. Okay, so the next property is pressure. So this is straightforward. So we define pressure as basically force over area. Okay, force over area. So we have the dimensions. It's straightforward. So basically, force is ma, right? Mass multiplied by accelerations multiplied by area. So if you consider dimensions, so that's actually mass is m, as acceleration is acceleration is lt minus 2, and then area is l minus 2. Okay, so we have the dimension is m, minus 1, then t minus 2, right? And the unit, if you look directly from here, so that's kilogram per meter per second squared, right? Okay, but force, of course, is also Newton, right, per meter squared, Newton per meter squared. And another name for Newton per meter squared, 1 Newton per meter squared is actually called Pascal. Pascal, right? Okay. Okay. So the next property is specific gravity and then specific volume. So let's look at specific gravity. Specific. Normally we use the symbol Sg for specific gravity. Yeah? So we define specific gravity as relative density compared to a reference density. Okay, so basically Sg in terms of formula, we say Sg is equal to rho, that's the rho of the fluid. Sg of the fluid is rho of the fluid divided by rho of a certain reference fluid, right? And it's quite common that we use the reference fluid as the density of water, right? And so roughly density of water is 1000 kilogram per meter cube, right? So what does it mean? So that means that if we use water as the reference, because water is the most commonly used liquid that actually available on Earth, right? So if you use water as the reference, so if we have a fluid which is Sg, which is less than 1, right? Sg less than 1, that means that density of the fluid is actually less than density of water, right? And conversely, if Sg of the fluid is actually bigger than 1, so that means that the density of the fluid is bigger than the density of water, right? Okay, so now if we put, let's say, 3 different fluid in a container, and the fluid actually have different specific gravity and different density, right? So let's say this is water, this is fluid 1, this is fluid 2, right? So since this one settled at the top water, so that means that the density is actually less than fluid 1 is actually less than density of water. So that means that Sg is actually less than 1, right? Of course, for water, Sg is actually equal to 1. And then for this fluid, since it settled below, so rho fluid 2 is actually bigger than rho water. So that means that Sg is bigger than 1. For example, if you take typical value for oil, okay, oil, Sg is equal to 0.9, right? And if you take for mercury, Sg is equal to 13. So that means that if you know Sg, then you can actually calculate the density. Okay, so let's say Sg is 0.9, so that means that the density is 0.9 multiplied by 1000 is 900. And then if it is Sg is equal to 13, so that means the density is actually equal to 13 multiplied by 1000, which is 13,000, right? Okay. And the last one for properties involving mass and weight is specific volume. Okay, you have learned about this in your thermodynamics actually. So normally we use a symbol small v, specific v. So we find this as volume per unit mass. Okay, so V is actually equal to volume per unit mass. Right, so if you recall, mass per unit volume is actually density. So this is actually 1 over density. Right, so the dimensions is so it's volume, so it's L3 and then M minus 1, L3 M minus 1, and the unit is actually meter cube per kilogram. So it's the reverse of density, right? Properties involving flow of heat. So first of all, if you recall what you have learned in thermodynamics, there is a postulate which is called state postulate, which says that the state of a simple compressible substance is fixed if we fix two independent variable, two independent properties is fixed, then the state of the substance is actually fixed, right? So properties involving flows of heat. Okay, properties involving flows of heat. So state postulate. Yeah, state postulate. So that means that if we have a simple compressible substance, okay, so if we fix two variable, okay, so if we fix two properties, two independent properties, for example, if we fix pressure and temperature, so that means that all the rest are already fixed, means that they are actually dependent on pressure and temperature. For example, the H, the enthalpy, the volume, everything's are already fixed. The densities are all fixed when we fix pressure and temperature. So if you recall, that's why when you use steam table, okay, if you recall when you use steam table, you just need to specify pressure and temperature, and then from there you can use a steam table to get the enthalpy, to get the entropy, to get the specific volume, to get the density, etc. Right. So that is state postulate. And then there is actually an equations that actually relates all of these properties with one another. So this equation is called equation of state. Equation of state, right? Equation of state. So it says that, let's say we want entropy, for example. So entropy is actually a function of P and T, right? Enthalpy is also a function of P and T. Okay, so there is equations which enable us to calculate how the properties are actually dependent on each other, right? So for ideal gas, so we have what is called the ideal gas equation of state. Okay, so ideal gas equation of state, which actually say like this: P is equal to rho RT. Okay, P is equal to rho RT, where P is actually the pressure, rho is actually density, and T is actually the temperature, right? So it means that if we know density and temperature, we can calculate the pressure, and conversely, if we know pressure and temperature, we can calculate the density, or if we know pressure and density, we can actually calculate uh, the temperature, right? And then R is actually what we call gas constant. Okay, So R for air, for example, R for air is actually the value is 287.058 joule per kilogram Kelvin. Right. Okay. Okay, so now let's look at specific heat. Specific heat is also properties which is involving flows of heat. Okay, specific heat capacity. So specific heat capacity is defined as the capacity of the substance to store thermal energy. Okay, the capacity of substance to store thermal energy. So it is the energy that must be transferred to a unit mass of a substance in order to raise its temperature by 1 degree. So that means that, let's say I have a substance, okay, so the mass is actually 1 kilogram. So I transfer energy E, right, in order to raise its temperature by 1 degree C, right? So this E is what we call C, right? C. So the units, because it's actually energy, so joule or kilojoule for a unit mass, kilogram and Kelvin, right? So if the process is actually occur at constant pressure, so we have specific heat at constant pressure, specific heat at constant pressure, and normally it's also called isobaric, okay, isobaric specific capacity, okay, and if the process actually done at constant volume, we have CV, so this is specific heat capacity at constant volume, okay, and sometimes it is called isochloric specific heat capacity, or sometimes also called isometric specific capacity, or sometimes also called isovolumetric specific heat capacity, right? Okay, so the ratio of Cp over Cv, okay, the ratio of Cv over Cv, normally we use a symbol, sometimes K, here I use K, and sometimes some book also use gamma for this, okay, so this is actually the ratio of Cp over Cv, so it's called isotropic exponent, okay, isotropic exponent. Since Cp and Cv is actually a function of temperature, gamma isotropic exponent will also be a function of temperature. Then the gas constant R is actually equal to Cp minus Cv. Okay, Cp minus Cv. Okay, so if you look at how isotropic exponent varies with the temperature for some of the gases, we can see that generally the isentropic exponent goes down. Okay, this is isentropic exponent actually goes down with temperature, which indicates that if you compare Cp and Cv on how it varies with temperature, Cv increases at a higher rate compared to Cv, so compared to Cp with temperature. Because of that, the ratio of Cp over Cv reduces. And so, for example, if I draw for air, if I draw for air, if I draw the graph of Cp and Cv with temperature for air, right? So this is 0, and this is all temperature higher than 0. You will see that, let's see if I plot, first of all, Cp is like that. Okay, and then this is Cp, and then Cv. So let's say it's like that, Cv, right? Since R is positive, Cp is always bigger than Cv, right? Okay, but the difference between Cp and Cv getting smaller as temperature increases. So that means that this one increases, both actually increases with temperature, but this one increases at slightly higher rate with T. And because of that, Cp over Cv goes down with temperature. Okay, the next property involving flow of heat that we're going to be looking at is specific internal energy U. And then the last one is enthalpy. So specific internal energy. Okay, normally we use the symbol U. So this is actually energy that substance possesses because of the state of the molecular activity of the substance. So if we have a substance with molecules inside the substance, it will have internal energy, and then the amount of internal energy dependent on the how active is this molecule inside the substance. So of course, at higher temperature, the molecular activity is actually more aggressive, right? So normally, so because of that, U is actually a function of temperature, or to be more specific, it is actually a function of pressure and temperature. At higher temperature, the molecule is actually more active, so the specific internal energy is actually higher, right? So the unit is actually joule per kilogram. Okay. And the last one that we're going to look at is specific enthalpy. Normally we use the symbol H. You have learned this in your thermodynamic. You have used enthalpies a lot in your thermodynamic, which is defined as the U, specific internal energy, that we defined just now, plus flow work. Okay, if you recall, in your thermo, this is actually U plus P multiplied by specific volume, right? So why is it that it's equal to PV? Okay, flow work. Why flow work is equal to PV? So just some small revisions to you. So let's say we have an area A, right, of fluids which move over a distance S that will create a volume V, right? So the flow work is actually equal to force multiplied by the distance traveled, right? Force multiplied by the distance traveled. So flow work per unit mass is actually equal to force multiplied by distance traveled multiplied by 1 divided by the mass, right? Okay. But from here we know that AS is actually equal to V, right? So I can actually write this. So I have S multiplied by S is V divided by A. Okay, so multiply 1 over mass. So I can rearrange this. So this is F over A multiplied by V over M. So that is actually equal to PV, right? Okay, so H is actually equal to U plus PV, right? Then we also know that PV is actually equal to P over rho also, since specific volume is actually equal to 1 over density, right?